Run of the river, as the name implies, means you have a river, and the river has a current inside that, and I can put a turbine, which could be horizontal or vertical, depending, of whether it's in the river, which at this or at the sea level, or that is from the mountainous area, and the river runs in the vertical direction. So the geography, it determines what kind of turbines to be used for the power plants. Another way to extract power from the water is through the waves. Waves have a mechanical energy. They are formed as a result of the wind flowing over the water, and the wind itself is a result of the non-uniform distribution of the ground. As the wind flows over it, the kinetic energy of the wind is given to the energy of the water, and that causes, a kind of sinusoidal wave to be generated on the surface of the water. As you go deeper into the water, then the size of these disturbances decrease, and eventually the effect of the wave is not found at the bottom of the sea level. When you are close to the beach, then there's a slope in the seabed, and so the water has to travel upward because the space is becoming limited. The amplitude increases, and the wavelengths of the wave decreases until eventually it cannot overcome the friction, and the wave falls over, and that's called a surf. Depending on the location, with different countries, they have different potential for the waves. The best kind of waves are in the Atlantic and the European coast of Atlantic. Atlantic is rather rough, so that's where most power is generated. The beaches are sandy and rocks, and that will also result in having bigger wave. UK, Ireland, Portugal, France, and Spain all are having beaches at the Atlantic side, and they produce most power. On the Pacific side, then the winds are smaller, the waves die down, and the amount of the power generated decreases quite a bit. As I mentioned, the surface waves have more energy inside them. As we go deeper and deeper, then the energy decreases, and at the bottom of the ocean, we only have a very small current that can be due to the fall and rise of the tide. The direction of the current will decreases, and that will be the source of power for underwater turbines. So this is an example of the underwater turbines, which is called the marine turbine. They operate in a similar fashion as the wind turbine. Some flow is passing through the turbines. The more flow you have, the higher the velocity of the current, and the more power you produce. In this case, because the water has a much higher density, about 1,000 times density of the air, then they would be more effective in producing power. So you need a much smaller turbine size to produce the same amount of the power in the air. One question often is posed to the designer is whether to build this wave stations near shore or the offshore. It depends. There's no simple answer. It depends on a number of factors. As you go offshore, of course, the waves are becoming larger, and so the efficiency of production of power will be larger also. But as you move offshore, the cost will go up, so there's a cost versus efficiency. Other advantages is the noise and visual impact will be minimal as we move away from the onshores to the offshore. How to produce power from this wave devices? These are some of the examples of generating of power. The diagram at the top left corner, it's called the TAPCHAN. It stands for taper channels. It's off the coast of Portugal. They built some experimental facilities. As the water hitting the rocky shore, then they have nowhere to go, and you can have a funnel, and the water flows over the funnel and pours inside a basin which has artificially been built. As the basin fills up, then they start to discharge through a hole at the bottom of that, and so now you have a head which is the size of this basin. As the water discharge goes back to the sea, then that head can be used to produce power by running a turbine. The diagram in the middle is basically a wave dragon called. So it's in the middle of the body of water. As the wave is hitting, the slopes of the side of this wave dragon, they overcome the slope and they go over the top. And again, they fill up in this reservoir, which is the top. And this reservoir in the middle, there is a hole, and the water will have to empty back into the ocean. But as the water empties back, it has some kinetic energy that can be used to run a turbine. The diagram at the right is also another example called Limpet 500. Limpet stands for Land Installed Marine Power Energy Transformer. It's built on the coast of Ireland, and basically very similar to the other type. The water, as it hits the shoreline, it has to go up the slope, but as it goes to a slope, it can turn a turbine that pushes the air to go up into a chimney and turn a turbine. As the water recedes back to the ocean, it produces suction. The air is being sucked in. As the air is being sucked in, then it will run a turbine on the way back and produces power again. Oscillating water columns, the examples of that are Archimedes wave swings. These are the number of the air-filled chambers submerged below the sea level, and is connected by movable float that oscillates up and down. As the waves move over them, then a series of linkages convert the vertical oscillation into the rotational energy, which in turn used to produce electricity. A pilot project off the coast of Portugal had been using 3 of such devices, produces 8 megawatt of electricity. Salter's Dock, again, is a concept that installed on a floating chamber connected to a fixed platform that swings back and forth with an incident wave. The bubbling motion is converted to rotational motion, which then runs a generator. Because of the high cost and large mass to power ratio, no full-scale device of this kind has ever been constructed. This one is a Plymouth wave energy converter. It's called the Sea Snake. And this is a semi-submerged articulated structure composed of a number of cylinder sections linked by hinge joints and moored to the ocean floor by long umbilical cord. As the wave passes by, the surface flexes and activates the hydraulic ramps that pumps high-pressure oil through hydraulic motors, which then drive the electric generator to produce electricity. The full-scale system that you see here uses 3 modules. Each of them is 130 meters in length and 3.5 meters in diameter. It's installed in the Portugal in 2008, operating as of 2008, and produces about 2.3 megawatt of electricity, giving the energy to about 1,500 homes.